Hi, I'm Dr. Courtney. Thanks for joining us at Carmel Academy, where our goal is to help you do science like a boss. And we know that we can do science like a boss because of what it says in the Bible. Genesis 1:26 says, "Then God said, let us make man in our image, after our own likeness, and let them have dominion over the earth." So we know that we're supposed to do science because we're told to be fruitful and multiply, fill the earth and subdue it. And science is a part of understanding how the created world works in ways that assist us in carrying out that creation mandate. And we know that we can do science because God said, let us make man in our image after our likeness. Now, who is God having that conversation with up there in heaven right before he creates mankind? Well, that's God the Father talking to God the Son and God the Holy Spirit as they decide to make man in their image. All right, so let's go ahead and address the topic for today's lesson. We're going to do an experiment regarding exothermic chemical reactions, exothermic chemical changes, and some more of the theory is covered in the instructions and probably in the textbook that you're using and so on. So let's skip to the chase of what's needed for the actual experiment. Well, we have an exothermic solution dissolving calcium chloride, which starts as a solid, dissolving it in water, and this yields calcium ions in aqueous solution, chloride or chlorine ions in aqueous solution, plus energy. And it's that release of energy that makes it an exothermic chemical change. So our hypothesis is that the temperature change of 100 grams of water will be proportional to the mass of calcium chloride dissolved in the water. Because if the energy is coming from the calcium chloride, as our theory suggests it is, then if you double the amount of calcium chloride, for example, you'll double the energy added to the water. If you double the energy added to the water, you'll double the increase of the water's temperature. So those are the ideas. Now, as a practical matter, we need a few things. One thing that we need is our laboratory thermometer. Another thing that we need is what's called a coffee cup calorimeter. It's convenient to use a styrofoam cup, and in fact you need several of them for this lab, would make it more convenient. And one of them you cut to make the top of the coffee cup calorimeter that works something like this, because you're going to put the water, the calcium chloride in the bottom cup, put the top on to help the heat be retained for longer inside the coffee cup calorimeter, and then we're going to insert the temperature probe in the top, and this extra Air Force Academy coffee cup over here is just for the purpose of stabilizing and balancing the experimental apparatus. Some other things that we'll need for the experiment: a graduated cylinder helps us measure 100 grams of water quickly. Because 100 grams of water is very close to 100 milliliters of water. And the calcium chloride comes in the form of damp rid, which can be obtained usually at a local hardware store or Walmart, and it's just a convenient source for calcium chloride. And the calcium chloride was chosen because it dissolves quickly in water and it makes a nice, strong exothermic reaction. And also need distilled water. And here it's important to have distilled water. It's very inexpensive and also available at Walmart and many other grocery stores. Because if you just get water from your tap or from other sources, there can be some impurities. And to do a good chemistry experiment today, we want to start with distilled water. So this is a fun experiment, so without further ado, we're just going to jump into it. Alright, well, here is our experimental setup for our exothermic solution experiment. And we have our table and kind of plan mapped out here in our lab notebook. 100 grams of calcium chloride, 100 grams of water with a increasing amount of calcium chloride, and this will enable us to record the initial temperature of the water before we add the calcium chloride, the final temperature, which represents how much it warms up due to the exothermic reaction of the dissolving of the calcium chloride, and then the change in temperature. And we're going to measure these temperatures in Fahrenheit because the resolution of our thermometer is 1/10 of a degree in both Fahrenheit and Celsius. But since Fahrenheit degrees are a little smaller, that gives us a little higher resolution, and we can convert to Celsius as an analysis step in our spreadsheet. Alright, so that's the experimental plan. We're using damp rid as our source of calcium chloride. This is available most hardware stores and Walmart. And as always in the chemistry lab, we use distilled water for our water because it just gives better, cleaner chemistry reactions because it's purer. I also want to let you know that you should store any leftover calcium chloride in a airtight mason jar or other airtight container, because this stuff is what's called hygroscopic. It attracts water. That's what it's sold to do. So if you don't seal it carefully in something that's won't let in moisture, it's going to end up collecting a lot of moisture, ruining your stock and possibly making a mess. Alright, so we've got our coffee cup calorimeter right here, and to save a little time rather than having to rinse out each coffee cup each time, we just have a number of coffee cups so that we can repeat the experiment with increasing amounts of calcium chloride without having to wash the calorimeter in between. And here's the top of our calorimeter, formed simply by cutting the bottom off of a coffee cup, making a hole in the middle, and this enables us to have a little better container in terms of holding in the heat long enough to get a measurement. Alright, so without further ado, let's go ahead and move forward with the experiment. The easiest way to get 100 grams of water is simply to weigh it. We get a good initial guess by using a graduated cylinder. It just gets us to 100 grams more quickly, because as it happens, 100 milliliters of water is really close to 100 grams. So we came up to 98.8, and we just have the dropper here. 99, 99.5, 99.7, 99.9, 100. Hey, and as we often do in the chemistry lab, we overshot a little bit. No worries, just take a little extra care, a little extra time. 100.1, 99.7. Come back up. We just want to do an accurate job as we can. Alright, so 100.0 grams of water. Go ahead and put that in our coffee cup calorimeter. And we need to take some care because our experimental procedure requires us to measure the temperature of the water before we add the calcium chloride, as well as afterward, because it's the change in temperature that's really the independent variable here that we're interested in. So just get that set up, and so you can see the Air Force Academy coffee cup is just sort of propping up the thermometer in a convenient manner, poking through the hole in the top. So our initial temperature is 52, and it's kind of bouncing between 52.7, yeah, let's call it 52.7 degrees Fahrenheit. And so now we can go ahead and prepare. Our first data point is for 2 grams of calcium chloride, and I'm using a more accurate scale here to measure out the calcium chloride, and that's simply because I happen to have it available, and having 2 scales available oftentimes just helps the experiment to move along a little more quickly. There would be very little compromise if one happened to just use one scale for the experiment. That one seemed to have a dead battery, so to keep things moving along, I just I grabbed the scale that doesn't have a dead battery. Alright, so we're going for 2 grams target, and I guess I overshot. So just take some out, make the adjustments as necessary till we get closer to our target quantity of 2 grams. Alright, so that's 1.960. Alright, so we got our 2 grams of calcium chloride, and we need to go quick here because the water is going to heat up and then the heat's going to start leaking out. So we just take some care, dump it down in there, give it a quick stir, and really without waiting too long, we want to, oops, forgot the top of our coffee cup calorimeter, get our probe in there, and it comes up to 55.4 degrees. Alright, so I've got that written down in the lab notebook. We can go ahead and get that out of the way and prepare for our next data point. Alright, so the next data point is going to be 100 grams of water again, and that's the same every time. But it's going to be 4 grams of calcium chloride for the next data point. Alright, overshot on the distilled water a little bit. Come up to 102. Not a big problem, just take some out. 99.9. Alright. A little bit of a challenge to get it exactly at 100.0, but just take a little care, a little time. Alright, 100.0 grams of water. Get that in there, go ahead and measure the temperature. We don't expect the initial temperature to change much from one trial to another because it's the room temperature. Pretty much possible that the lights or something else might cause a little bit of variation, you know, 1/10 or 2/10 of a degree or something like that. Start weighing out our calcium chloride. Go ahead, let's record the initial temperature, 52.7 degrees Fahrenheit, same as it was for our previous trial. Make sure that our scale's in the right measurement mode, grams. And now we're just aiming for 4.0 grams of calcium chloride. Alright, so without further ado, get the top off the coffee cup calorimeter, get the calcium chloride added, give it a quick stir. Get the top on the calorimeter and the measurement probe in place. And watch it carefully until it gets to its maximum, 56.8. 57.0, and it looks like 57.0 is the peak. Now if we sat there and watched it, it does start to cool off quickly, and what that indicates is that our coffee cup calorimeter is not a perfect insulator, right? Some heat is getting back out into the room, and this thing's going to drop back down to room temperature. It might take a half hour or so to get all the way back down to room temperature, but the point is the experiment will go a little better if you watch it, work quickly, watch it, and take the peak temperature rather than lollygagging around, as it were. Alright, so let's go ahead and get a clean coffee cup. Let's start working on the next data point. Now we're going to go for 100 grams of water and 6 grams of calcium chloride. Alright. So now we're at 99.6 grams of water. Add a little with our dropper. 100.0 grams of water. Get that over in the coffee cup calorimeter. Get the probe in place to measure the water temperature, the initial temperature that is, before we add the calcium chloride. And while that's coming to its place, we can turn our scale back on. I think it's got a battery saving mode. It keeps turning it off. And we need to make sure it's in gram mode. And now our target mass of calcium chloride is 6 grams. And one of the things that you'll occasionally encounter is that the particle size for the chemical you're weighing is bigger than the finest point of resolution on your electronic balance. I don't know how well you can see that on the camera, but those chunks of calcium chloride are pretty big. So, you know, we're not trying to get it to the last milligram, but what we're trying to do is get within, you know, plus or minus whatever one of those particles weighs. So let's go ahead and make sure we write down the initial temperature, 52.7 degrees Fahrenheit. Take off the top of the coffee cup calorimeter. Add the 6 grams of calcium chloride now. Give it a stir. Alright, get the top of our coffee cup calorimeter back in place. And pay attention while it comes up to its peak temperature. 57.3, 57.5. Alright, so let's go ahead and leave that in place while we see if it's going to come up anymore, while we keep maybe weighing out our next 100 grams of water for the next trial. No, it looks like 57.5 is as high as it's going to go. So we go ahead and record that in our lab notebook. Let's go ahead and we're at 98.2 for our mass of our water. .6, 98.7, 90, 100.0. Alright, well it did end up coming to 57.7, so I'm going to go ahead and record that in our lab notebook because it came up a little more. Go ahead and get that coffee cup out of the way, get the new coffee cup in place. In the meantime, go ahead and make another adjustment here on our quantity because it bounced up to 100.1. Alright, 100.0 on the quantity of water. Go ahead and get that in there. And now we'll go ahead and get the thermometer in place so it begins to come up to temperature. And this is now 8 grams is now our target weight, our target mass on the added calcium chloride. Make sure we're in gram mode. Alright, 8.000 grams now. So if you notice, our temperature, maybe warming up under the lights a little bit, is now 53.0 for our initial temperature. So we'll go ahead, get that written down, get 8 grams of calcium chloride in place, give it a good stir, get the lid and the temperature probe back in place, and now we're waiting for it to come up to temperature with 8 grams of calcium chloride. And while that's happening, we can go ahead and be efficient in our time here and work on weighing out our next water. Alright, so it had come up to 62 degrees, which may have been the peak, and it might be going back down now, 61.8, 61.7, and so on. So I'm going to go ahead and take a break from preparing the next water. I'm going to go ahead and write that down as 62.0 degrees Fahrenheit for the 8 grams of calcium chloride. And let's go ahead and we can now keep preparing our 100 grams of water for our next data point. I gotta be more patient. I keep ending up at 100.1. Which, you know, in this case, when it's as easy to go backwards with the dropper as it is to go forwards, it's not like it's a disaster. It just takes a little more time. Alright, now I'm at 99.9. The thing is laughing at me. Alright, now we're at 100. And now we're at 100.1. Alright, so let's go ahead and get the coffee cup calorimeter out of the way with the 8 grams. Let's go ahead and get the 100 grams of water in place for our next measurement. Our next measurement is going to be 10 grams of calcium chloride. So let's get to measuring our initial temperature, and let's go ahead and weigh out our, oops, this scale keeps turning off. And what happens if you turn the scale on with, you know, a beaker or whatever sitting there, is it automatically zeros, this scale does, when you turn it on with the whatever's sitting on it. So you don't want any of your chemical already in the beaker when you turn it on, otherwise your zero's off. So your measurements would be off. So now our target is 10 grams of calcium chloride, 9.4. Alright, now we're just a hair over 10, so we'll take off a few of these little flakies. Put a few of the flakies back. And we're trying to get it not necessarily within 1 milligram, but we're trying to get it to, you know, plus or minus 1 flake. Alright, so our initial temperature there is 53 degrees Fahrenheit, 53.0. Write that down in our lab notebook. Get the top of the calorimeter out of the way. Get the 10 grams of calcium chloride added. Stir. Now we can get the top of the coffee cup calorimeter back in place to make our measurement. And now we're watching it as it comes up as usual, and we're trying to catch it at the peak temperature, 62.4, and we'll just keep an eye on it while we measure out our next 100 grams of water. Alright, 62.4. Overshot on the water a little bit. Okay, we came up 62.6 there. It was brief, but it was 62.6. So if it doesn't get any higher, I plan to write down 62.6. Alright, now it's holding 62.6 a little more constantly here for a few moments. Not for a very long time, but now it's back down to 62.4. Once it starts going back down, I'm pretty confident it's reached the peak temperature, and then it's losing heat through the calorimeter. So I'm going to write down 62.6. Alright, 62.6 degrees Fahrenheit for that data point. And so let's go ahead and get this coffee cup out of the way. Get our final coffee cup in place. And so this data point is going to be 12 grams of calcium chloride in the 100 grams of water. So that's the 100 grams of water in place. Now we're measuring out the 12 grams of calcium chloride. We're to 11.9, 12 and a smidge, back off a little bit, 11.9 and a smidge, 12.065. Now we're getting to the point where take out a couple more flakes and we should be right on it. 12.05. Again, take out a flake or two, you undershoot. Oh, 12.000. Alright, sometimes you get it just right. Alright, go ahead and add our calcium chloride. Give it a good stir. And get that calorimeter top back on. Get it in place. Since that's our last data point, we're just here watching the temperature go up now. 67.2. Now it's already dropping back. Oh, 67.1, 67.2. Well, it's just bouncing around a little bit, so we'll go ahead and give it a minute and let it decide what it wants to do. 67.4. 67.2, 67.4. So it looks like it's going back down now. So we'll write down 67.4 as the final or peak temperature. So always a good thing when you have all the data in the notebook, so we can work on now cleaning up our laboratory area and shift our emphasis to analyzing our data. Oh, hang on. While I'm sitting here talking, it went to 67.6. Aha. And you know, when you need to make a correction in a lab notebook, the procedure is to line out the number that's not perfect and write in the corrected number. You never want to erase or line it out so completely that you can't see what it was before the change. That's just a principle of good science, so that there's a record that, you know, gee whiz, 57.5, nope, scratch that out, 57.7 or 67.4, and then we changed it to 67.6. So just like kind of a record, that's how you make corrections in a lab notebook. Okay, well here is the spreadsheet we're working on with our data from the exothermic solution experiments. And all we've done a lot of spreadsheets in earlier labs, is we've got the independent variable, which is the mass of the calcium chloride in this column. We've got our original measurements for the initial and final temperatures in these two columns. And we use these two columns here to convert the temperatures from Fahrenheit for the initial temperatures to Celsius and for the final temperatures. And here, if you recall from our experimental design, our dependent variable is the increase in temperature, delta T, which we call in del T there, in degrees Celsius. And then these is just the computations, which is the final temperature minus the initial temperature for each quantity of calcium chloride. So that's just the data analysis that gets us to the point where we have our independent variable and our dependent variable, and we can copy and paste them over into our graphing program, which is what we have here. And at first blush, this doesn't look much like a line, much less a proportionality, but let's go ahead and insert the trend line, and we want the trend line to go through the origin, so we set the intercept equal to 0, and that's because our hypothesis isn't simply that it's linear. Our hypothesis is that the change in temperature is proportional to the mass of the solute that we added. Okay, so now we've got the trend line, and I guess with a line to guide our eye, it looks like, well, that's a little more linear than it looked without the line. We look at the r squared, and the r squared is 0.93. Now, in a lot of areas of science and for a lot of kinds of experiments, a 0.93 r squared value is suggestive of a pretty good relationship. But if you recall, for some of our experiments more on the physics side of the physical science class, Hooke's law and some other experiments, our r squareds are like 0.99 and change. So 0.93 is a lot lower than we're used to seeing for linear or proportional relationships. So there's one other way to consider this, and you know, I wouldn't get too enthusiastic. This certainly doesn't strongly support our hypothesis, but there's another analysis step we can do to help us frame our discussion or our conclusion with regard to how strong this hypothesis might be supported. And that's to compute what's called residuals. And to do that, one takes the best fit formula, and so I'm going to go ahead and take the slope here with all the digits. And we bring this back over into our spreadsheet, and you compute what's called residuals. And a residual is the difference between your experimental value, in this case the delta T, and the theoretical value, which is the theoretical value comes from multiplying that slope by the independent variable. So first we want the experimental value, so that's element B3, and then we subtract A3 times the slope that we had. And so we can go ahead and cut and paste this formula all the way down. So for each data point, each measurement, each quantity of calcium chloride, this residual represents the difference between the experiment and the theory. And let's go ahead and let's format a little better there. We don't need all those digits to see what's going on. Maybe 3 digits will be a pretty good indicator. And so one of the things you're thinking about with regard to the residuals and whether or not your model fits your data well enough to say your hypothesis is supported is, are your residuals smaller than or about the same size as your instrumental uncertainty? And our instrumental uncertainty in this case is about 1/10 of a degree Celsius. So when we have, you know, this value, 1/10 of a degree, 1/10 of a degree, almost 3/10 of a degree, 3 of our data points out of 6 have residuals that are much larger than our instrumental error. So, and there, you know, errors could creep in other places in the experiment. In this experiment, for example, I wonder, you know, if the calcium chloride dissolved fast enough. I wonder if maybe heat was leaking out through the coffee cup calorimeter to prevent it from being a perfect experiment. So while, you know, this disagreement and the coefficient of determination of 0.93, that isn't so bad that I would say that the hypothesis is disproven, and I wouldn't say that the hypothesis is unsupported. But given all the factors, I'd say that our experiment and the resulting data only provide weak support for the hypothesis. So we do suspect on theoretical grounds that the hypothesis is probably true. We just didn't do an accurate enough experiment to support the hypothesis as strongly as a more accurate experiment may have supported the hypothesis. There's nothing wrong with that. But in science, when your experiment does not provide very strong support for the hypothesis, you just want to try and articulate that clearly and be honest about it. We could have done a better experiment here. Wow, that was a fun experiment. I really enjoyed it. I enjoy the challenges and the insights that come from studying and learning about God's creation. And one thing I want to point out from this experimental experience is that it's okay to make mistakes. And you'll notice we made a couple of them. Some of them during the experiment itself. One of them with the calculations regarding the data analysis. But if we're paying attention, we want to be honest. We want to notice we made the mistake as early on in the process, because when you notice that you make a mistake early on in the process, it tends to be easier and more recoverable. The greater difficulty occurs in science, like a lot of real life, is when we pretend we didn't make a mistake, or when we're not being careful enough, so that we get further and further downstream before we acknowledge our mistake and take corrective actions. The longer it takes to put our corrective actions in place by acknowledging our mistake and trying to fix it, then usually the more time and effort and money it takes to fix whatever the mistake was in the first place. Thanks for joining us today at Carmel Academy. I'm Dr. Courtney.